Welcome to this scientific lecture on engineering prompts that enable artificial intelligence systems to identify research gaps through comparative analysis of methods and assumptions. Before we dive into prompt engineering, we must understand what constitutes a research gap. A research gap represents an area where current knowledge is insufficient, contradictory, or where methodological approaches fail to address critical questions. Visualize the landscape of knowledge as interconnected domains. Research gaps exist in the spaces between established methodologies, where different approaches fail to overlap or where contradictions emerge. Comparative analysis across methods is not merely academic exercise. It reveals fundamental tensions between approaches, exposes hidden assumptions, and illuminates paths forward that single-method analysis cannot detect. Consider a methodological landscape where four distinct approaches exist. The intersections and tensions between these methods reveal where our understanding breaks down and where new insights might emerge. Now we examine the architectural components necessary for prompts that facilitate deep comparative analysis. These components must work synergistically to guide artificial intelligence toward meaningful gap identification. The prompt architecture consists of four fundamental layers. Each layer builds upon the previous, creating a hierarchical structure that guides the artificial intelligence through increasingly sophisticated analytical operations. The context layer provides the epistemological foundation. It defines the domain boundaries, historical development, and theoretical frameworks within which comparison will occur. Context encompasses multiple dimensions. The historical trajectory informs how methods evolved. Theoretical underpinnings reveal philosophical commitments. Practical constraints shape application. Empirical evidence grounds claims in observation. Method specification demands precision. We cannot compare what we have not clearly defined. Each method must be described along multiple axes, including assumptions, procedures, validation criteria, and scope of applicability. Two methods are specified along identical dimensions. This parallel structure enables systematic comparison. The assumptions underlying each method become explicit. Procedural differences emerge clearly. Validation approaches can be contrasted. Scope limitations become apparent. Assumptions represent the hidden foundations of methodology. They are often implicit, taken for granted, and rarely questioned. Yet assumptions determine what questions can be asked, what evidence counts, and what conclusions are valid. Visualize methodology as an iceberg. The visible portion represents observable procedures and results. But the bulk of methodological commitment lies hidden beneath the surface in assumptions. These assumptions about causality, measurement, and validity fundamentally shape what the method can reveal. We can classify assumptions into several categories: ontological assumptions about what exists, epistemological assumptions about how we can know, methodological assumptions about valid procedures, and practical assumptions about resources and constraints. These assumption categories orbit around the core research question. Each type of assumption constrains the investigation differently. Ontological assumptions determine what entities we admit into our explanatory framework. Epistemological assumptions delimit our claims about certainty and justification. The comparison framework provides the analytical scaffolding. It must specify dimensions of comparison, criteria for similarity and difference, and mechanisms for detecting contradictions or complementarities. Four key dimensions structure comparison. Strength refers to explanatory power and predictive accuracy. Limitations identify boundary conditions and failure modes. Validity addresses internal and external validity concerns. Scope defines the range of phenomena addressed. Methodological tensions arise when different approaches make incompatible claims or rely on contradictory assumptions. These tensions are not merely errors, but often reflect deep philosophical disagreements or unresolved empirical questions. When two methods produce conflicting results or rest on incompatible assumptions, a tension zone emerges. This zone is precisely where research gaps become visible. The tension demands resolution through new theory, better measurement, or methodological innovation. Gap detection criteria must be explicitly defined. What constitutes a gap? We identify several types: empirical gaps where data is lacking, theoretical gaps where explanatory frameworks are absent, methodological gaps where tools are inadequate, and integration gaps where synthesis is needed. 4 gap types require different detection strategies. Empirical gaps involve missing observations or measurements. Theoretical gaps reflect absent explanatory mechanisms. Methodological gaps indicate inadequate analytical tools. Integration gaps show failure to synthesize across domains. We now synthesize these components into a coherent prompt structure. The prompt must guide the artificial intelligence through context establishment, method specification, systematic comparison, and finally gap identification. The prompt flows through 5 phases. Context definition establishes the analytical space. Method specification makes approaches explicit. Comparison analysis reveals relationships. Gap identification highlights deficiencies. Synthesis produces actionable insights. Context definition must be precise yet comprehensive. We specify the research domain, relevant literature, historical development, current consensus, and outstanding controversies. This creates the knowledge landscape within which methods will be compared. The domain forms a hierarchical structure. Core concepts branch into related subdomains. Each subdomain connects to relevant methods and assumptions. This network structure makes explicit how different approaches relate to the broader knowledge landscape. Method specification requires decomposing each approach into constituent elements. We identify core algorithms or procedures, required inputs and outputs, underlying mathematical or logical framework, validation protocols, and known limitations. Parallel specification enables direct comparison. Each method is decomposed along identical dimensions. This structural alignment reveals where methods diverge and where they converge. Differences in algorithmic approach, validation strategy, or limitation profiles become immediately apparent. Eliciting assumptions is perhaps the most challenging aspect. Assumptions are often tacit, embedded in practice, and taken for granted. We employ several strategies, examining what must be true for the method to work, identifying implicit premises and justifications, and analyzing what the method cannot accommodate. Assumptions exist in concentric layers. Explicit assumptions are openly stated. Implicit assumptions are inferable from method description. Hidden assumptions remain unacknowledged. Core assumptions are so fundamental they shape what counts as a question. Effective prompts must probe all layers. Comparison execution requires systematic analysis across multiple dimensions simultaneously. We employ matrix comparison where methods form rows and comparison dimensions form columns, revealing patterns of similarity and difference. The comparison matrix organizes analysis. Methods occupy rows. Dimensions of comparison occupy columns. Each cell represents a specific comparison along one dimension for one method. Patterns emerge. Methods may cluster on some dimensions, while diverging on others. Convergence indicates where different methods agree, suggesting robust findings. Divergence reveals where methods conflict, highlighting areas of uncertainty or gaps. Both convergence and divergence are informative for gap detection. 4 methods occupy different positions in methodological space. Where they cluster, convergence suggests reliability. Where they separate, divergence indicates unresolved questions. The convergent zone represents established knowledge. Divergent regions represent potential research gaps. Gap detection employs multiple heuristics. We identify unexplained variants where methods fail to account for observed phenomena. We detect assumption conflicts where methods rest on incompatible premises. We locate methodological blind spots where no existing approach applies. 4 gap detection mechanisms operate simultaneously. Unexplained variance identifies where current methods fall short. Assumption conflicts reveal fundamental disagreements. Methodological blind spots highlight inaccessible phenomena. Integration failures show where synthesis is needed. Explanatory coverage refers to the proportion of observed phenomena that a method can adequately explain. Gaps emerge in regions of low coverage where phenomena exist, but explanations do not. The total phenomena space represents everything we wish to explain. Current methods cover a substantial region shown in green, but a gap region in red remains unexplained. This visual representation makes coverage limitations explicit and guides future research directions. Assumption incompatibilities arise when 2 methods rest on logically contradictory premises. For example, One method may assume deterministic causation, while another assumes stochastic processes. Such incompatibilities represent deep gaps requiring theoretical resolution. 4 common assumption pairs reveal incompatibilities. Deterministic versus stochastic assumptions about causation cannot both be true. Reductionist versus holistic assumptions about explanation conflict fundamentally. These incompatibilities mark deep theoretical gaps requiring new frameworks. The final phase synthesizes findings into actionable insights. Not all gaps are equally important. We prioritize based on several criteria: theoretical significance, practical impact, methodological feasibility, and integration potential. Identified gaps are prioritized by size and color coding. High-priority gaps in red represent areas with maximum theoretical significance and practical impact. Medium-priority gaps in orange are important but less urgent. Low-priority gaps still merit attention. This prioritization guides resource allocation. Theoretical significance assesses whether filling the gap would advance fundamental understanding. Gaps that challenge core assumptions or enable new predictions have high theoretical significance. Gaps that merely refine existing knowledge have lower significance. Theoretical significance forms a hierarchy. Paradigm-shifting gaps at the apex fundamentally alter our understanding. Theory extensions add new domains or mechanisms. Refinements improve precision. Minor details matter but are less transformative. Prompts should guide identification of high significance gaps. Practical impact evaluates whether addressing the gap would enable new applications, solve existing problems, or improve decision-making. Gaps with high practical impact justify immediate attention, even if theoretical significance is moderate. Practical impact manifests in multiple domains. New applications emerge when gaps are filled. Existing problems become solvable. Decision-making improves with better understanding. Processes become more efficient. High-impact gaps deserve priority, even if theoretically incremental. Methodological feasibility determines whether current tools and techniques can address the identified gap. Some gaps are important but currently intractable due to measurement limitations, computational constraints, or theoretical underdevelopment. Feasibility exists on a spectrum. Green gaps are immediately addressable with existing methods. Yellow gaps require some methodological development. Orange gaps are challenging, but possible with significant effort. Red gaps are currently intractable. This assessment guides realistic research planning. Integration potential assesses whether filling the gap would enable synthesis across previously disconnected approaches. Gaps with high integration potential are especially valuable because they can unify disparate research streams. 4 disconnected research domains remain isolated until a bridge gap is identified and filled. Filling this gap enables integration, creating a unified framework. Such gaps have multiplicative value because they enhance understanding across multiple domains simultaneously. We now construct the complete prompt integrating all components. The prompt must balance comprehensiveness with clarity, providing sufficient structure to guide analysis while allowing flexibility for unexpected insights. The complete prompt architecture contains 7 integrated components flowing from context establishment through synthesis. Each component builds on previous ones, creating a logical progression from domain understanding to gap identification to actionable recommendations. Let us apply this framework to a concrete example, comparing climate modeling methods. Different approaches make different assumptions about spatial resolution, temporal dynamics, feedback mechanisms, and parameter estimation. 4 major climate modeling approaches exist. Global climate models with high resolution use physical equations. Statistical downscaling employs empirical relationships. Earth system models integrate biogeochemical cycles. Regional models focus on specific areas. Each makes distinct assumptions about relevant processes and appropriate scales. Different methods assume different appropriate temporal resolutions. Some model processes at hourly scales, others at daily or monthly scales. These assumptions reflect beliefs about which temporal dynamics are essential and which can be aggregated. Temporal resolution choices span orders of magnitude from hours to years. Each choice represents an assumption about which processes matter. Hourly resolution captures diurnal cycles, but is computationally expensive. Annual resolution misses seasonal dynamics, but enables long-term projections. Gap Optimal temporal resolution remains unresolved. Spatial scale assumptions also vary dramatically. Global models sacrifice local detail for planetary coverage. Regional models provide fine-scale resolution, but require boundary conditions from global models. This creates a fundamental tension between generality and specificity. Three spatial scales represent fundamental trade-offs. Global coverage provides planetary context, but coarse resolution. Regional models improve resolution, but sacrifice global consistency. Local models maximize detail, but require extensive boundary specifications. Gap: no unified multi-scale framework exists. All models require parameter values, but estimation methods differ. Some use historical data calibration, others use physical theory, still others use expert judgment. These differences reflect uncertainty about parameter identifiability and measurement. Four-parameter estimation approaches coexist without clear superiority criteria. Historical calibration assumes stationarity. Physical theory requires complete mechanistic understanding. Expert judgment introduces subjectivity. Ensemble averaging masks underlying uncertainty. Gap: no principled parameter estimation framework spans all approaches. Our comparative analysis reveals several research gaps in climate modeling. Temporal and spatial scale integration remains problematic. Parameter estimation lacks unified theory. Uncertainty quantification differs across methods. These gaps impede model intercomparison and confidence assessment. Four major gaps are identified and prioritized. Scale integration and parameter estimation theory are high priority due to theoretical significance and practical impact. Uncertainty quantification is medium priority. Validation methodology is important, but lower priority. This prioritization guides research investment. The climate modeling example illustrates the general approach. Define domain, specify methods explicitly, extract assumptions systematically, compare across dimensions, identify tensions, detect gaps, and prioritize for action. This framework applies across scientific domains. The framework applies across diverse domains, from medicine to engineering. Each domain has multiple competing methods with different assumptions. Comparative analysis reveals domain-specific gaps, while illustrating universal principles of gap identification. Several factors determine success in engineering comparison-driven prompts for gap identification. Precision in method specification prevents ambiguity. Explicit assumption elicitation reveals hidden commitments. Systematic comparison structure enables pattern detection. Clear gap criteria guide identification. 4. Success factors must be present. Precision ensures methods are clearly defined. Explicitness makes assumptions visible. Structure enables systematic analysis. Clarity facilitates interpretation. When these factors align, artificial intelligence can effectively identify meaningful research gaps.